All right, this is section 4.2, the strength of acids and bases. So a major goal of this topic is to learn how to read the table, relative strengths of Bronsted Lowry acids and bases. That's page 6 of your data booklet. All right, so take that one out. We're going to be referring to it the whole time while we're doing this. So the strength of an acid is determined from the concentration of our hydronium ion. So H3O plus concentration, that ionization, that amount of that concentration of these ions, that is what gives us the strength of that. So how much it releases those H3O plus ions is what makes it a strong acid or a weak acid. So the H3O plus mice also what gives the acid their properties, right? This is the sour taste, the colors, and the indicators of reactions with metals. So this is what makes an acid is this hydronium ion, this H3O plus. We went over that a little bit in the last one. All right, so strong acids, right, and weak acids. So in everyday English, if we talk about something that's strong and something that's weak, like a strong cup of coffee, it'd be a concentrated cup of coffee. A weak cup of coffee would be a less concentrated cup of coffee, right? So with a strong acid, it's not the same thing. So strong acids refer to the degree of ionization of the H2O plus that we're making. So HCl is considered a strong acid, and when it ionizes, it's going to push all the way to the right. Look at the one-way arrow. So it's a one-way ionization, and it's going to ionize 100% in solution. It says disassociation on your notes. I think that's a typo. Disassociation is for ionic compounds. Ionization is for molecular compounds like acids. Anyways, this is going to ionize 100% in solution, and it's going to push it all the way to the right. A weak acid, these are which we have less than 100% is ionized, and less than 100% is like is very generous. It's much less than that, right? So it's like you're not going to like 99%. You're going much less. We'll worry about these calculations later on, right? And the actual number of what we're doing because it all depends on their Ka value. So weak acids, they do not dissociate fully. Usually around 5% or less is going to be ionized. These at equilibrium with the reactants and are heavily favored. So weak acids all have these double arrows, right? So major difference, strong acids, 100% dissociation, have the one-way arrows. We have virtually zero HCl and 100% H3O plus. These ones have a double arrow, right? So even if we look at a bottle of HCl, there's virtually zero HCl in a bottle of HCl, right? If that makes any sense. So whatever concentration of HCl, it's all in H3O plus and Cl minus, right? So important concept to get through. The one-way arrow, strong acids ionize 100%, weak acids ionize less than 100%, right? And usually much less, and we'll worry about that later on. And these guys have the double arrows. All right, so again, to go over this, we have HCl added to water is going to be H plus and Cl minus. One-way arrow, 100% ionization. CH3COH, this is vinegar, acetic acid, added to water. It's going to form an equilibrium. So we have the acetate, the H3CO minus, and our H plus. And basically, we're going to have very little of this actually being produced. We'll worry about the numbers later on, but it's gonna make this equilibrium. Like they're gonna be going back and forth, but this ionization is going to be less than 100%. Similarly, with a strong base NaOH added to water, going to Na plus and OH minus. Again, strong bases, one-way arrow, 100%. We're gonna have this Na plus, the spectator floating around, and the OH minus is what makes the strength, what makes it a base, right? Weak base, again, we're going to be making, it's going to be going in, equilibrium with the reactants, right? Again, we're going to be making very little of these guys, and it's going to be mostly in our reactants. All right, so strong acids and bases go 100%. Weak acids and bases ionize very little. All right, so hopefully you have this table out. If you don't, go and grab it. Put it on pause and then come back to it. So different things we want to notice on here. So the name of this table, we'll call it the acid-base table. That's technically called, I guess, at the top, the relative strengths of Bronsted-Lowry acids and bases. Things to notice on the table, this bar on the left-hand side. So the strength of the acid. So we have weaker acids at the bottom, strong acids at the top. Similarly, we go for the strength of base, weak bases here, right? Start there, and then stronger bases as we go down. So they're opposite to each other's, the opposite with each other. So we got the acid, the chemical formula as we go down, right? The name up here on the this column here, and we got the bases, right? No name for the bases, but that's okay. The also this one here, this number, this letter here, Ka, as you might have guessed it, it is the KQ for the acid. So we'll talk a lot about these later. So they all have each of these different these acids have a Ka value. There's a Kb for the bases, and we'll talk about that in our next section. We need to do a simple calculation to find it out. These five at the top, I'll talk about them. So 2, 3, 4, 5. So these, well, I guess the sulfuric acid. I guess these top six. These are all the strong acids, so they're equally strong, right? Notice they're one-way arrows for these guys. So the Ka is going to be really large. So Ka is still product concentration over reactant concentration, and our Kas, everything's going to be in the form of products, and there's virtually zero. So it's very large. Some textbooks say they're undefined because you have basically an like you have infinite slope, right? Because you have almost zero of this and all of it's over here. So you're going very, very large. All right. So just very, very large, and they're equally as strong, right? So we're not going to say our perchloric acid is stronger than our nitric acid or anything like that. They're all equally as strong because they're all ionizing 100%. All right. So that's what they call the leveling effect, right, on your notes here. So each these top six strong acids dissociate or ionize 100%. They level or are in equivalent strength. All right. So one thing to notice with this one are HSO4 minus. This so it's just releasing the 1H plus with their H2SO4, but this HSO4 minus, we'll notice it down here at the 1.2 times 10 to the -2. All right. So it then goes and releases another one. So it becomes a weak acid over here. All right. All the rest of them, they're just, we call them spectators. They're just floating around, not doing anything in the solution. All right. So leveling effect, all six of these are strong. Weak acids, they're going to form an equilibrium. All right. Also looking at the table. So if we were to write this out fully, they didn't put the water in it. So this would be a perchloric acid. So HClO4 plus water is going to go to a hydronium atom, H3O plus. So all these H pluses as we go down this column, they're all H3O pluses, right? So you're added in water. So the iodic acid HiO3 plus H2O is going to go to H3O plus, right? So I think they're just saving space and less writing on it. But you have to, if you want to be complete, you put the water and the hydronium ion because the H plus, any H plus in water is going to make your hydronium ion. So be aware of that. So the bottom two never act as acids in water. So if we look at way down here, O2 minus H plus, right? We see the one-way arrow over here. So these two, NH2 minus going to H plus. So they're never going to act as water. They're never going to go into equilibrium here. So these are strong bases. So these are very small. These guys will form bases. So any O2 minus is going to make an OH minus in solution. NH2 will make an NH3, and then it'll go into equilibrium with the NH4, as you see, 5.6 times 10 to the -10, that one there. All right, so these bottom two, we notice the one-way arrow is going the other way, so don't be confused with that. All right, bases, strong bases. Like I said, they ionize or dissociate 100% in solution. So we got the sodium hydroxide going to Na plus and OH minus, right? So this Na plus, this is going to be a spectator just flowing around. OH minus, anything that ends in an OH is going to be a strong base. There are some exceptions, but we're not going to try to trick you with any ones in this course. So if you see it ends in an OH, it's metal OH, then it's going to be a strong base. All right. So weak bases, these are ones that ionize less than 100% solution. So just like the the weak acids, right? These ones are going to ionize less than 100%. So we have the NH3 plus, H2O goes to NH4, and your OH minus. So notice you have the the base, it's conjugate acid, and then conjugate base. So you still have those those on those pairs, those conjugate pairs like you would before. So that's the equilibrium that those guys are going to go into. All right. On the table found above OH minus on the right side. So all these guys, these are going to form weak bases in water as they go from right to left. So like they're going to go by the same pattern, right? You add the weak base to water, you're going to be forming its conjugate acid and the base, right? So if we go back to this one, weak base plus water, conjugate acid, and your OH minus. So that's how we're going in the reverse one. So weaker bases at the top, and then it gets stronger and stronger as you go down on the right side. All right, so to summarize this, strong acids or strong bases, they're going to dissociate or ionize 100%, right? So their strong bases go 100%, strong acids go 100%. Notice the one-way arrow. Weak acids or weak bases, less than 100%. And we notice the double arrows, right? They're going to form the equilibrium. We're going to be doing Ka calculations with acid, Kb calculations with base, very similar to your KEQ questions. Okay, so something to note, adding a strong acid to water produces H3O plus. Adding a strong base to water produces OH minus. The stronger the acid, the greater the concentration of H3O plus, and then similar, the stronger the base, the greater the OH minus. Okay, relative strengths on our Ka table, right? Acids at the top, strongest acid, weakest acid as we look on the left, bases, weakest base to the strongest base on the right. Double arrow for our strongs, one-way arrow for our strongs, double arrows for our weak. In an equilibrium reaction with two acids, so we have our HCN and F minus, right? IHF and Cl minus. The stronger acid is going to dissociate more. All right, so the Ka value that you see on the right, that is its amount of ionization or dissociation or whatever. So the stronger one is going to push the other one. It's gonna push its equilibrium to the other side. All right, so this next little section is determining whether reactants or products are favored in an acid or base reaction. So if we look at this one, HCO3 plus or HF is going to go to H. It's going to be in equilibrium with H2CO3 and your F minus. So both of our acids, if we look, so we got the HF as an acid, H2CO3 also an acid, and those are the bases. So there's the HF, it's conjugate base, H2CO3, and its conjugate base on this side. So what we have to do is find out which one is pushing the other one to the other side. So which one is able to donate that proton easier? And it all depends on their Ka value. So the stronger acid wins out and pushes the proton in a greater extent. So we're going to have a situation. So HF, if you look on your table, right? HF is a stronger acid, right? So HF is at 3.5 times 10 to negative 3. And HF at 3.5 times 10 to negative 4, and H2CO3 4.3 times 10 to negative 7. So our HF is higher on the left, so it's going to push more to the right. All right, so we have so this one we'd say that our products, the forward reaction is favored, so our products are going to be favored in the reaction. Another way to saying it, I think maybe they mentioned this in the book, they go, it's survival of the weakest, right? How Darwin was survival of the strongest. This is survival of the weakest. HF is going to be pushing over here, so our products are going to be favored because HF is a stronger acid, able to push its proton over to get rid of its proton more than our H2CO3. All right, so just like in our KEQ, a higher KEQ, products were favored, lower KEQ, the reactants are favored, like less than one, the reactants are favored. This one would have a higher KEQ. for this one. So we'd be pushing in the product's direction. All right, so the side of the reaction with the weaker acid is always favored. Stronger acid, like I said, donates a proton more readily, causing the other side, the weaker side, to be greater in concentration. All right, so let's try some of these ones. All right. So maybe pause it and we can come back and look at it. All right, so with this one, we have NH4 and on the left and our H3O plus on the right. So H3O plus, this is going to be the strongest acid in solution. We see it up at the top at K. Our Ka for this one is 1.0. So we're going to push it over here. So we're going to say the reactants are favored in this one. All right, look at the next one. So compare the two acids. So we look at H2S with the acid, HS its base, NH4, then NH4 with the acid. So we're looking for our H2S on the table. So H2S 9.1 times 10 to the negative 8. And our NH4, we can see is just below that at 5.6 times 10 to the negative 10. So our H2S is a stronger acid, right? So it's going to be pushing more. So we're going to say that the products are favored in this one. All right. And our last one. So we got the H2PO4, right? That's the acid, its conjugate base. And so that means the H2S is it. We've already found the H2S, 9.1 times 10 to the negative 8. H2PO4 right below it. So we're going to be pushing. So the H2S is a little bit stronger than our H2PO4. So we're going to be pushing, and the reactants will be favored in this one. I can show you later on how to do calculations for this, but this is the easier way to do it. We can do calculations to do the relative KQ for this one. Extra problems from your work. So there's just a few at the bottom to see whether reactants or products are favored. Just getting used to your table. I would suggest doing some of these just to get more familiar with how your tables looked out, the strength of the acids, the strength of the bases, and how the equilibriums get pushed to each side. All right. Let me know if I have any questions.